thank you very much for inviting me. It's a pleasure to be here. I want to talk about inattentive decision-making in changing environments. And just by way of background, I'm a macroeconomist at the University of Maryland, so I'm going to be bringing more of a macro perspective to the things that we've been talking about. And so before I talk about inattentive decision-making, let me just spend 30 seconds on attentive decision-making. So in the classical model of decision-making, when faced with any decision situation, one should, as we've discussed, obtain perfect information, eliminate all uncertainty, fully evaluate all the options and their consequences, and end up with a decision that maximizes individual welfare. Moreover, when faced with any change in the situation, however small, however frequent, one should, again, immediately obtain perfect information, eliminate all uncertainty, evaluate all options and their consequences, and come up with a decision that maximizes individual welfare and celebrate. So there's, of course, a lot of situations where people don't literally do this. And so there are a lot of patterns that seem to suggest deviations from this normative model of behavior. One pattern that I want to focus on, and that is particularly relevant in macro, is that of infrequent adjustment. And so at the individual level, if you think about an individual firm or the managers in an individual firm or an individual consumer, we see that many decision variables are adjusted discretely, infrequently, in a lumpy fashion, even though market conditions are changing pretty much continuously. And this applies to prices of various goods and services. It applies to wages, hiring, inventories, capital investment, size and composition of portfolios, and so on, right? So this is such a pervasive feature of economic data that a lot of attention has gone to figuring out how to model this adjustment. And this is kind of a really core issue in macroeconomics because different models of adjustment have different implications for how shocks are transmitted in the economy at the business cycle frequency and how things like monetary policy and fiscal policy can or cannot stabilize demand fluctuations. Okay, so just to give you kind of the motivating example that will be running through my talk, if you are familiar with models of infrequent price adjustment, you might be familiar with kind of the two classic types of models of infrequent price adjustment. The menu cost models, in which price adjustment is state dependent. These models assume that you will only adjust if the value to you of adjusting is enough to cover a cost, like the menu cost, the cost of reprinting the menu. These types of models will in general predict very small degrees of rigidity in aggregate prices, and so very little inefficiency from nominal price rigidities, and very little ability of the central bank to actually intervene and stabilize fluctuations. At the other end, you have Calvo, or random adjustment probabilities, right, where the firm will adjust its price with a constant probability, regardless of the state of the world. And these models will imply significant nominal rigidities, right, and significant ability of the central bank to influence aggregate outcomes, right? So we kind of want to understand which model we should use for aggregate and policy counterfactuals. Okay, so one approach in macro is to rationalize things that don't look like the classical model of decision-making, so in particular in this case, to rationalize an action within classical optimizing frameworks, right? And I think it's fair to say that still the benchmark today in macro models is the classical model of decision-making. And so in the context of an action, you might posit a fixed adjustment cost, right? So the menu cost model. And the challenges to this model are, I want to highlight kind of three challenges. First of all, you get an action in experiments where adjustment costs have been, as much as possible, minimized. So it's not obvious that the inaction is coming from a literal cost to be paid in order to, change your decision. Second, models in which you have a fixed adjustment cost generate counterfactual predictions in terms of the distribution of adjustment dynamics. So for example, in the data on price changes, we see that firms implement both very, very small price changes and very, very large price changes. That's kind of hard to square with a model in which there's a fixed cost of adjustment, and so you shouldn't see firms be willing to adjust by a very, very small amount because that shouldn't generate such a big gain so as to cover the cost of adjustment. Okay. The third issue is that these fixed
Unless the environment changed by about.
Yes, that's right. That's right. But you see kind of small, if you look at kind of small
so conditional
shocks.
On small changes in environment.
Continuous, yeah. Because you're going to hit your boundary of adjustment, and so as soon as you hit it, you're going to adjust. You're not going to wait for a bunch of small shocks to accumulate too much. A third issue with these kinds of models is that they all assume perfect repricing conditional on adjustment, right? So you might not adjust your price all the time, but when you do decide to adjust for whatever reason, whether it's for a Calvo reason or for a menu cost reason that the value of adjusting is high, then you compute perfectly the value of adjusting, and you compute perfectly the value of charging different prices, and you pick deterministically the P star that maximizes your continuation value from that point onward. Right? And as we've talked extensively here, this is at odds with overwhelming evidence from many, many contexts that actions are actually based on dispersed beliefs and that they're only noisily related to optimum. Okay, so I'm just going to show you kind of 3 pictures for these 3 challenges to the standard menu cost model from an experiment with Mel, Ka, and Mike. So here we had subjects try to forecast a Bernoulli, random variable. And so here's the evolution of the Bernoulli. So let me kind of go slow because there's a lot going on here. So here's time, right? Trials. They did 1,000 trials, so a lot. And then here's the realization of this Bernoulli that they were trying to forecast, right? So it started at around 0.7. And then on every trial, there's some tiny probability, like 0.5%, that the value of the Bernoulli will change. It'll be drawn uniformly from the unit interval. So in this case, it just so happened that a lower value was drawn, and then other values like that. Okay. How do they learn about the potential value, about the value of this Bernoulli? Well, they see ring draws from a box in which the proportion of green rings is equal to this probability. Right. So as they see the ring draws, they update their beliefs about what the Bernoulli probability is. So here's in blue the Bayesian forecast. So this Bayesian observer would start at 0.5 because they know that the Bernoulli is drawn from the unit interval uniformly. And then with every ring realization, they'll update their beliefs a little bit, right? And they'll update their forecast a little bit, and they'll track the black line quite well. I'm sorry. Okay. I'm not giving any concerts anytime soon. Okay. Okay, so they track this quite well. It deviates, of course, sometimes from the state, from the hidden state, because of just the randomness in the ring realizations. Okay. And now in red, I've plotted a subject from this participant. Like now, this guy started at 0. Okay, that's okay. But then he adjusts really quickly, right? So he realizes that the probability is probably pretty high. So he quickly adjusts, and then he stays put for a long time, right? Then, after a while, he realizes he needs to adjust again. And see, so there's this kind of step pattern. This is what I mean by discrete or lumpy adjustment. Okay? See that some of the adjustments are very small, whereas some of them are very big. Right? This is what I mean by the adjustment does not seem to be determined by some fixed cost of adjustment. Okay? So that's one discrete adjustment. Here's the distribution, so variable adjustment. How often, how much do they wait until they change their forecast? So sometimes they don't really wait at all, right? Sometimes they wait a really long time. So it's not like a time dependent, I'm going to change every 10 ring draws. That doesn't work either. Or firms, this also holds for firms changing prices. It's not like firms change prices every year. Maybe typically they change them every year, but within that typical, there's a whole distribution of adjustment spells. And then here's the...
Sorry, but the previous slide, the big change was when there was a big change in environment. So it went, so it's not when there was a small change in environment, which was exactly my point in the previous comment. So.
Yes. No, that's right, that's right. So I think what you would say, what I would say is that if you just posited big changes, that wouldn't be enough to justify the discreteness. So, now I'm in trouble because I have to find a counterexample. You're right, of course, but we tend to think of small accumulation of shocks as demand and cost conditions kind of change continuously over days and weeks and months, right? As opposed to suddenly, I mean, you know, COVID was a different kind of animal, but typically in the day-to-day business cycle type fluctuations.
Yeah, it's a continuous war, which this one isn't. So, okay.
Okay, and then here's the distribution of adjustment sizes. Again, you see a big mass at or around, or not exactly at, but around 0, right? So this is the distribution conditional on adjusting, which suggests that it's not a fixed menu cost. And then you also see very large adjustments. Now, if I were to plot the distribution of adjustments for this shock process, so for this exogenous state, if I were to plot the distribution of adjustments from a menu cost model, I would get much kind of a totally different distribution. I would get no mass in here, and I would get bimodal, I would get these two spikes at the SS adjustment bands. Okay, and then third, stochastic forecast. So we've talked a lot about this already. In this experiment, we see that if we plot the subjective forecast against the Bayes optimal forecast, there's clearly not a deterministic relationship, not even close, right? There's huge dispersion of forecasts around the Bayesian optimal. Although the Bayesian probability does predict the subject's forecast, it's very, very noisy. Okay, so the hypothesis is that these patterns reflect information-constrained decision-making. And so what I want to talk about is how a model of rational inattention of the decision-maker to the real-time environment could generate stochasticity, discreteness, and inaction. And so I'm going to start with kind of a very simple static rational inattention problem, talk about stochasticity. And then I'm going to talk about a dynamic rational inattention model and talk about infrequent stochastic choice. I'm going to set that in a monetary economy. So I'm going to torture you with a little bit of macro. Hopefully not too much. All right, so static decision problem. So let's suppose a decision maker faces a decision that leads to some uncertain payoff. So the actions are denoted by A, and this set curly A. The payoff is a function u that depends both on the action and on the realization of the state. The state is drawn from some distribution P, and let's suppose that the agent knows the actual distribution from which the state is known. So without anything else, the agent could just say, all right, I'm going to take the action that is optimal under my prior, some A bar, that maximizes my expected payoff under the prior. Right? And then the question is, should the decision maker try to differentiate states more? How much more? And at what cost?
All X there is at the end of the line.
Oh, yes. Sorry, because I'm summing over them.
Oh, maybe you mean the sum. Anyway, okay.
No.
No,
I think
this doesn't depend on X.
no. Yeah. Okay. Okay. So should you differentiate how much more and at what cost? Okay. So then we need to get a notion. We need to get a notion of uncertainty about this random variable and how we might reduce this uncertainty. So rational inattention in a nutshell is kind of a very, I think, very elegant abstract model of information-constrained decision-making that gives us a way to maximize information, to optimize over information choices. So the basic idea is that information is abundant. You can learn about everything that could ever possibly matter to you in any context. There's no constraints on that. But it's hard, it's costly for you to gather it and process it and make sense of it. You can also, not only is information out there available, so not only is the supply kind of unlimited, but you also, let's suppose you also can choose very, in a very sophisticated way how much of this information you want to acquire, what type of information you want to acquire. You can choose to ignore some things, you can choose to combine things, whatever makes sense to you given your incentives, your objectives. Okay, so we can apply this kind of cost-benefit analysis. And we're going to have an environment in which the decision makers understand the rules of the game. They understand the laws of motion of the environment that they're in. They understand their objective function. So they know their U, they know the stochastic processes that govern uncertainty in their environment, but they don't have free real-time knowledge of the realization of these random variables that are hitting their payoffs. Okay, so then they choose kind of how much to pay attention real time to these realized states. Okay, so Chris Sims proposed using information theory to formalize this kind of idea of information acquisition. So he said, let's think of decision makers as dedicating limited capacity to processing information that's relevant to their decisions, and let's apply Shannon's information theory to endogenize their information choices. So information theory, which formally models physical limits to the rate of transfer of information, he said, may provide a way for us to capture the intuitive appeal of the signal extraction story. So this is going to be a signal extraction story in the state, while neither introducing implausible constraints on the observability of data. So it's not that data's not out there. There's tons of data out there. Nor abandoning entirely the strategy of modeling behavior using optimization. Okay, and so what is information theory? So information theory tries to solve the fundamental problem of communication of messages from one point to the other. So you can think of an information source that's generating some messages. These messages have to be transmitted to a receiver, to the destination, right? They have to be transmitted through a channel. Okay, so you might have to kind of compress the message to make sure that it fits through the channel. That's one. You might also have to kind of distort the message so that not only does it fit through the channel, but it can be understood given that the channel might itself have some noise, right? Okay. And then the receiver is Bayesian, right? So this part, the decoding of the message that's sent, is very easy. It's simple. You just apply Bayes' rule to find your posterior belief about what the message was that was transmitted. Okay? So Shannon says the fundamental problem is we want to reproduce a message from, or transmit a message from one point to the other. I find this next sentence very funny. So frequently the messages have meaning, suggesting actually the meaning doesn't matter, right? It doesn't matter what we're sending. What does matter is what is the probability with which you can expect different messages to be sent, right? So what matters is that the message is one selected from a set of possible messages. Okay. Why does that matter? Because what we're going to use as a measure of uncertainty about a random variable is this object that he called entropy. So funny story, he was struggling with what to name this, and the mathematician von Neumann said, you know, just call it entropy because nobody knows what entropy is anyway. Yeah. So it's all good. Okay, so he called this entropy. So we have this object that's the expected value of x over x of the log of 1 over p of x. Okay, so this is the prior uncertainty that a decision maker has about some random variable x. Y log over 1 of px. So, you know, let me just say very quickly, this is basically a limit.
Sorry, something I don't understand.
Yes.
On the right-hand side, you would expect it hangs out. On the left-hand side, it happens. That is that variable.
That's a
Oh,
big
you're
X.
right.
That's a big X.
Well, this should really be p.
The random variable.
Oh, P, all right.
It should. So I'm following the notation in the information theory literature, but where they use the random variables. But yes,
And then it would be a
it's not. It's just a p. Yes.
Or it would be a capital X. The
Yes,
random variable
yes.
name.
Yes.
Or an X with a tilde on it.
Good. So this is a limit to how efficiently you can transmit messages regarding the realizations of x. Right. So what this is saying is, if I want to transmit to you messages from some distribution p of x, the way I should encode these messages is I should use really, really short code words for realizations that are very common. So for example, in the English language, the words I, we, yes, no are very short because we use them a lot, right? How short should they be? Well, in the limit, they're going to end up being log of 1 over the probability, right? And conversely, messages that are really rare, realizations that are really rare, like heterogeneous, are going to be much longer, right? That's kind of an efficient coding algorithm. Okay, so we have this prior uncertainty over the random variable x, and then we can say, okay, what if if you receive, or if you learn the realization of some other random variable S, right, can I compute how much residual uncertainty you have about X? Well, yes, I can compute the conditional entropy, right, that says, on average, over the distribution of S's, how much does each S reduce your uncertainty about X? Okay, and then now we have a measure of information, mutual information, that's just the reduction in entropy, in the entropy of X, from seeing the S realizations. Okay, and so that's going to be this expected value over the joint distribution of S and X of the log of the conditional over the unconditional distribution. Okay, or the posterior over the prior. Okay, I want to talk a little bit more about mutual information. So you can manipulate this in different ways, and it's got very intuitive, expressions. Okay, so we have the reduction in uncertainty. You can also write mutual information as the Kullback-Leibler divergence of the joint distribution of the signal and the state from the product of the marginal.
Is it for those theta's? Does they appear suddenly? Do they mean anything?
They appeared because I want to differentiate this from P of X alone.
No, P of X and S. It's a probability of X and S.
Fair enough. Yeah,
Okay.
fair enough.
There's nothing.
All I want, yeah.
Okay.
All I want is this is the joint, this is the marginal, and this is the conditional. I'm gonna bore you with tildes. Kind of, okay, so Kullback-Leibler divergence. What is this? Well, this is kind of a measure of distance between distributions. This is saying if the true distribution were P double tilde, how wrong would you be if you use the product of the marginal? If you were really wrong, that means the joint is really different from the product of the marginal. If you were not wrong at all, that means the joint is the product of the marginal, i.e. these two variables are independent, i.e. the information you learn about X from S is nothing, is 0, right? Okay. Another way to look at mutual information is to say that it's the average Kullback-Leibler divergence of the conditional from the prior, of the posterior from the prior. Okay? Good. Okay, so, okay, of course, I of XX is the entropy. It's 0 if they're independent. It's symmetric. It's going to be convenient to use this symmetry property. The information that X tells me about S is the same as the information that S tells me about X. Okay? And if I receive information about X at a rate that's lower than X's entropy, then I've had some data loss. I've had some compression, and that's going to lead to data loss. Okay, so now going back to my problem of maximizing the expected value of that U of A and X, suppose the decision maker can reduce their uncertainty about X by designing, I'm going to call it a representation that is basically a signal, right? So a set of signals S, a conditional probability Q of seeing signal X in state S in state X, for each X and X this time. And an action rule, A star, could be stochastic, it won't be, that maps the signals into the actions to maximize the expected payoff, net of the cost of reducing this uncertainty. We're going to assume the cost is linear in the mutual information between the signal and the state. Okay, so here's my cost. Okay, and we're going to assume there's no cost of implementing the desired action, so for now I'm not going to have any menu costs. Okay, it's going to be convenient to rewrite mutual information as the average Kullback-Leibler divergence of the conditional distribution of the signal relative to the unconditional distribution of the signal relative to the marginal. This is the object that I'm going to be solving for, so I'm just going to write the problem in terms of this Q of the signal. Okay. Okay. Now, a simplification before we go further. I've been talking about signals and then actions. It turns out the optimal solution generates a distribution of actions with the same mutual information as the signals. So there's no point in different...
Two signals that equal the same action, you join them.
Exactly, exactly. No point in differentiating among signals that result in the same action. Uh-oh. Okay. There's also no point in randomizing actions after you received a signal, because if you randomized actions, then you might as well have acquired less information to begin with. So we can rewrite the problem directly in terms of choosing the distributions of actions conditional on the state. Okay, so I'm going to abuse notation eventually. And I'm going to... this is extreme rational inattention right here.
The computer is still working?
No, it's blank.
Are you going directly from the USB?
No.
No, the computer is not working. So
Yeah, it's just what you see is what
it
is.
connected to the, maybe its battery is gone or something? No, the computer.
I mean, this is blank too.
You can back on for it.
Good idea. Where's the keyboard? Oh,
I called someone.
Oh,
it's still blank.
No, but.
So it's me, not you.
okay. Good. Maybe you didn't like the computer.
Okay, so we're going to solve for this distribution Q. I'm just going to keep going. Okay. Sorry. So we're going to solve for this distribution Q, trading off the benefit of more accurate decisions against the cost of more accurate decisions. Okay, so here's my problem. So maximize expected utility net of the cost. And here's my solution. Okay, so this is going to look very familiar to you. This says that the probability of the decision-making maker taking action A in state X is high relative to the unconditional probability of taking this action if the gain relative to the cost of differentiating this action in this state is high relative to the average gain of taking actions in the set in this state of the world. So if, in other words, if this action gives you a good payoff, you're more likely to choose it, okay? But this differs from the expressions that we've seen in the last couple of days because it has this, this prior term here, right? So it says, I start with a prior belief of what the optimal actions are, right, unconditionally. I know that, you know, most of the time I charge high prices and occasionally I'll charge a low price, right? And so my tendency is going to be to charge high prices, right? The more information I acquire about the state, the more I can deviate in my conditional probability from this unconditional prior. Okay.
So just to make sure, Q bar of A is the probability of playing A in the Bayesian optimal decision with prior P. Oh.
Yeah.
Okay.
Yeah.
Okay.
Yeah. Good. Okay. So for any, if I give you a Q bar, you can then compute a conditional Q. And then the question is, what actions should I take with positive probabilities, positive probability, right? So then we can use this complementarity slackness condition, where I have this term Z that says, you know, pick any action in the curly set, right? Any possible action at all. The actions that are going to be taken with positive probability, I'm going to be indifferent among them in terms of the value over the state, right? And then the actions that are not charged with positive probability, that are not taken with positive probability, are going to be weakly dominated by the actions that are taken with positive probability. Okay. Okay, so let me give you a really simple illustration. So suppose we have just a quadratic objective function. Suppose we have a uniform X distribution with mean 100. And let's start with a no information solution. There is such a thing, right? If the cost of information theta is high enough, I might decide to just go with my prior. It's just not worth it for me to even bother, right? And then, you know, there's an algorithm we can run to solve the problem, and I'm going to show you this Z function, which shows you how the support evolves, okay? So let's plot the z function for different values of a, starting with a big theta, a big cost of information. Okay. And so let's zoom in a little. Whoopa. Okay, sorry. Okay. Okay, so at high enough theta, the decision maker just takes action a bar at 100. And then as you lower theta, the decision maker differentiates more and more among states and adds more and more points of support. This is kind of cool. Okay. And as you lower theta, each of these supports is going to be associated with more and more precise conditional distributions, right? So when the state is low, you're going to tend to have your Q concentrated around here, but it's never going to be deterministic, right? There's always going to be some chance that you're going to get a signal to charge a price over here, to take an action over here, because I kind of rushed here, right? For actions taken with positive probability, Q is never 0 and never 1, right? As theta goes to 0, as the cost of differentiating across states goes to 0, then this converges to the degenerate optimal action in that state, the full information solution. And as theta grows to infinity, then this converges to just the unconditional Q bar, where I'm not differentiating across states at all. Okay, all right. Okay, so now with this illustration, what I want to do is, okay, so in short, you can think of rationally inattentive choices as being based on compressed, noisy representations of the environment. That's very useful, but what about delayed adjustment and infrequent adjustment? This is kind of a big deal in macro, and I started with this. So for that, we need to go to a dynamic environment. And in fact, Chris Sims's motivation for bringing rational inattention to economics was about aggregate dynamics, right? So the central issue in macro is that not only do you see lumpy adjustment at the individual level, at the firm level and household level, but if you then take these variables and you aggregate them and you plot these aggregate variables like aggregate consumption, aggregate investment, right, aggregate prices, the aggregate real wage, they have these kind of hump-shaped delay dynamics in response to shocks, right? So how do you get these kind of hump-shaped dynamics? Well, the modern macro literature, so like I said at the beginning, the default in macro is to try to work within the classical model of decision making and then introduce some costs, wedges, something that can generate, for example, delayed responses within the optimizing framework, right? So Chris Sims's proposal was to say, look, if we introduce these kinds of information frictions, then we might be able to replace all the little adjustment costs and wedges and habits in modern macro models and fit sluggish aggregate dynamics with just kind of one friction, okay? So in the dynamic setup, what we want is a setting where the choice of the optimal representation becomes forward-looking, right? So recall we have, this is our static problem. We're maximizing expected utility net of the cost of differentiating in state X, right? Differentiating the action in state X relative to the unconditional probability of doing that action. And so now, you know, we have to think in the dynamics about the information of the decision maker. So one question that comes up right away is, you're doing a repeated problem, right? You're doing a repeated optimization. You're setting prices every week, right? Can you condition on past signals or the passage of time for free or not? So suppose yes, suppose you can remember perfectly the full history of signals that you've received. Then the cap on, or the cost of uncertainty reduction, is going to be applied to new information relative to the prior that you have entering the period. And this prior at the beginning of this period is the posterior at the end of the previous period and contains all the history of signals that you have up until that point, right? If you have this kind of a model, then you get these dampened, delayed, hump-shaped responses to shocks, and there's a bunch of work on that area. Now, alternatively, suppose no, you can't condition, because memory is also costly, and in fact, if anything, it might be even harder to remember a vector of past signals than it is to look out the window. So suppose there's equal cost per unit of entropy reduction for both looking out the window and looking inside your long-term memory. Then you can also have a setting where you get infrequent adjustment, right? As in micro, so you can get both the micro and the macro patterns. Okay, so let's talk a little bit about the first one, and then I'm going to spend most of the time on the second version with no costless recall. Okay, so version 1. Okay, so we can't do, so dynamic problem with costless recall, we can't just do static optimization anymore because the history of actions forms, which remember, forms a prior. You're going to combine it via Bayes' rule, so this is Bayesian model. And you're going to get a posterior based on which you make a decision. So the acquisition of information becomes a dynamic problem because information has continuation value. Okay, so you're going to maximize your expected discounted utility, right? Net of the cost of differentiating in state t. So of taking action AT conditional on having taken the vector, this vector of actions in the past, where this is the history of all actions that you've taken up until t minus 1, relative to your prior, which also conditions on this vector. Okay. Okay. So let's put this. Oh, before we put this in a simpler framework, the simplification that we can still keep talking just about actions. We don't need to go states, signals, and then signals to actions, continues to hold. So Steiner, Stewart, and Marteka proved this. You need to have cost linear in Shannon mutual information, so we're going to do that. And so then you can solve via two-step optimization. Fix the marginal distribution, solve for the optimal conditional distribution to maximize the net expected payoff, and then given the solution for the conditional distribution, solve for the optimal marginal distribution to minimize the mutual information between the conditional and the marginal. Okay, why to minimize the mutual information between the conditional and the optimal? Why are we doing this? Well, so think about what you want to do. You want to be really smart about how you use information that you already have, right? So information about the environment and the past actions that you've done, you want to use them to get you as close as possible to the optimal action in this period without actually conditioning on the state in this period. Okay? And so you're going to get as close as you can to the optimal, to the conditional, without actually conditioning. What does that mean? Well, then that means that you want to pick a Q bar that has the smallest Kullback-Leibler divergence to the conditional as you can. Okay. So for a given Q bar, I'm going to pick the Q that maximizes my expected value. And then I'm going to keep iterating to try to get my Q bar as close as possible to the conditional. Like if I know there's no way I'm going to charge negative prices, I don't need to have a prior Q bar that puts any weight on negative prices, right? I'm just going to forget about that part of the space and focus only on positive prices. I'm going to come back to this default later. Okay, so the solution to the dynamic representation with free recall has a very similar flavor, right? So the conditional deviates from the marginal when the value of deviating in this state is large relative to the unconditional.
Here, x sub t is the vector of the past observation.
No, super.
T, yeah.
Super is the state, and A is the observation. A is the actions which you can observe. You never learn the state.
Holy story.
Okay,
A is history of
Yeah,
actions.
so A super t is the whole vector
Yes.
of the past action.
Yes.
Okay, fine. And can you say again what was your capital Q?
I'm saying for a given capital Q, find the optimal conditional. And then use that conditional to find the Q bar that minimizes the mutual information
Is
between.
it the Blount article?
Yeah.
Ah, okay.
That's right.
Okay, so there's nothing more than that you put in this two steps.
No. Yeah. Okay, good. So, and so so here's the continuation value of information, right? So you're maximizing this. What is the value? Well, it's the value of taking action A, T, in state X superscript T, given that I've done history AT minus 1 up to yesterday, is given by the current flow payoff of taking this action in this state. This could be superscript, it doesn't matter, but I've just made payoff only conditional on today's X, that's fine. So, okay, so current payoff plus the discounted expected value of entering next period state with now a superscript T, with now a new history of actions that has this action in it, the current action in it, right? So this AT today has continuation value, and so I'm thinking about that when I'm choosing what actions to take today. Okay, and then what's the continuation value? Well, it's the value under the assumption that I'm going to keep optimizing in the future forever and ever. Okay, good. And then I have this complementarity slackless analogous condition. And then you get these kind of really nice hump-shaped responses. So suppose you have an X that is an AR1. You get an impulse in period 1, and then this decays at some rate. Well, the solution, the decision maker's response is going to be, partial on impact. Then, as they get more information, they respond more and more and more, and eventually they decay. Right? So this is exactly the kind of aggregate macrodynamics that we want to see in our models. Okay, but this doesn't generate infrequent adjustment, right? In every period, you get a bit of information, you combine it with your prior, you make a new decision, right? You make a new Q, you choose a new QT, right? So that the distribution of actions conditional on the state is changing in every period. Okay, so can we get lumpy infrequent adjustments in a rational intention context? Yes.
Before you
yes.
get to that, earlier you said that in the case with perfect recall, you do get delayed response. Is that lower curve what you mean by delayed?
Yes.
You're not responding fully.
Yes.
To the
Yes.
Okay.
Yes. Okay, other questions? Okay, so now I'm going to go to macro. Okay, so given discrete adjustment, let's break the decision, let's break the analysis up into two separate questions. Let's think about what determines when adjustments occur, and what determines what action is taken when adjustments occur. Okay, this follows very much the logic of existing models in macro of infrequent adjustment, right? So if you think about the menu cost model, that's exactly how it's set up. It's set up, you're going to think about whether or not to adjust, and then you're going to think about what to do when you adjust, right? So let's follow that model. And let's suppose that the decision maker cannot condition on past signals, actions, nothing for free. In fact, there's an equal cost, okay? So there's no side information, okay? Everything that the decision maker wants to learn about, they have to learn about through this interface with their environment. Okay, and I'm going to apply this to monetary economics and ask how flexibly do prices adjust to shocks, and can we actually use data on price adjustment to estimate the thetas, to estimate how severe information frictions are in at least in this price setting context. Okay, so I'm going to talk about this recent paper that I have with Camilo Morales Jimenez, who's at the board. Okay, and so in this paper, what we're going to do is give a time series of the degree of nominal price rigidities in the US. We're going to have a general equilibrium macro model in which we're going to have pricing frictions that combine kind of menu costs and information costs. And we're going to estimate the model on macro series of economic activity, inflation, and on data on how the distribution of price changes evolves over time. So if I have a series for the frequency, the cross-sectional frequency of price changes over time, what does that mean about how flexible prices are? Frequency, size, standard deviation of price changes, all these moments of the distribution of price changes. And along the way, we kind of reassess some aspects of the conventional wisdom on price rigidity and what drives price rigidity. Okay? Okay, so allowing for imprecision in both the timing of price changes and the chosen price levels. We're going to have two key objects. So up until now, I just had this object that was the conditional probability of doing an action, conditioning on the state. Now I'm going to have the action be the price. I'm still going to solve for the conditional probability of charging a particular price given the state. But I'm going to have kind of a dual decision problem. I'm also going to solve for the probability of adjusting the price to begin with. I'm going to denote that by this function lambda t. Okay? And I'm going to introduce menu costs. So up until now in the static model, I didn't have any menu costs. Now I want to introduce menu costs as well. Okay, so let's kind of put this in context in terms of the basic time-dependent and state-dependent models. If you think about the time-dependent Calvo model of adjustment, what does that model say? It says, well, the optimal policy is characterized by an adjustment rule that says I'm going to adjust with a probability lambda bar constant no matter the state. Right? And then I also have a repricing rule, P star, that is chosen to maximize. So if the Calvo fairy hits me on the head, then I reprice, I calculate the price that maximizes my continuation value, given A, my apologies for using A now as the state, my idiosyncratic conditions, like let's say this is my productivity, and X, the aggregate conditions. So how strong is demand, how high is aggregate economic activity. Okay? And so Calvo is very popular in macro. It's very tractable. It generates large price rigidities. It generates prices that, because are adjusted only infrequently and with a probability that is independent of the state, it generates prices that, you know, could be very, very far from the optimal, right? Even if you're losing money like crazy, unless the Calvo fairy hits you, you're not going to change your price, right? And so if you get stuck with a low price, you're going to be producing a lot because you stand ready to supply whatever, to meet whatever demand walks in through the door, right? So that's going to mean your price is rigid, your quantity is adjusting a lot. That means large price rigidities, that means large effects of monetary policy.
For the non-economist,
Yes, sorry.
sorry, what's the motivation for saying that this lambda bar is independent of other
Of the state?
variables?
Yeah, so, I mean, if you looked at, so in the early days of the data on price setting, there was some evidence that firms tend to change prices about once a year. And so that was kind of taken as the conventional wisdom of how big this lambda bar should be to imply, you know, frequency of, or to imply duration of about once a year. And it was also thought that, you know, firms change prices largely because of maybe idiosyncratic conditions, right? They're worried about their local market conditions, and maybe with respect to aggregate shocks, the probability of adjustment is not going to be that sensitive to the aggregate shock, right? And then finally, it's just very tractable, right? And it generates the kind of non-neutrality that you know we tend to think is realistic in terms of how the Fed can affect the economy, right? Because the way the Fed works is they manipulate nominal interest rates, and if prices were flexible, then prices would adjust. There would be no effect on real interest rates, so consumption and investment and all that wouldn't respond, right? The Fed affects nominal interest rates. Prices are rigid. That means real interest rates and real quantities adjust. That's non-neutrality in a nutshell. So we're really, you know, in monetary economics, we're really dependent on this P star not being continuously updated. Okay, so this is Calvo, and then of course people are going to say, well, but this is very ad hoc. Why are you assuming this constant? Okay, it's simple, it works great, but maybe we should have a menu cost model, maybe we should have an optimization problem, and maybe we should have the optimal policy be characterized by an adjustment rule that says adjust with probability 1 if the value of adjusting relative to the value of keeping your price unchanged exceeds some fixed cost, kappa, and adjust with probability 0 otherwise, right? And then if you decide that you are far enough from the optimal, then you're going to have a repricing rule that's the same as the Calvo repricing rule, right? So again, you're going to choose a price that maximizes the continuation value given your idiosyncratic state, like your own marginal cost and your own demand, and given the aggregate state of the economy, okay? And so this has the advantage of having optimizing foundations, right? It responds to the Lucas critique. What I want to do now is talk about a way to generalize this to a stochastic version in which we want to think about the adjustment rule as adjusting with a probability that is increasing in the value of adjusting. And I want to think about a repricing rule that specifies a probability of charging a particular price that is increasing in the value of charging that price in a particular state. Right? So we can allow for this generalization, and then we can take this to the data and ask, does the data support such probability, like a probability of adjustment that is weakly or steeply increasing in the value of adjusting? Does the data support a repricing rule that is probabilistic or not? And how much noise is there around each of these decisions, right? We can estimate this. And that's what we're going to do in this paper. Okay. I think it's really interesting that the macro literature has spent an enormous amount of time thinking about the adjustment rule, thinking about who adjusts when, how much selection is there in the adjustment rule. So the reason these two models give such different implications for macro dynamics is because there's a lot of selection in the menu cost model, in the fixed adjustment cost model. The only people who are adjusting are the people who are far enough away from the optimal to make it worthwhile. That means they adjust by a lot, right? Whereas in the Calvo, some people adjust by a little, some people adjust by a lot, because it's random, right? So Calvo has no selection on adjustment. The pure menu cost model has a lot of selection on adjustment. And there's been a ton of work on second, third generation menu cost models trying to dampen this selection on the adjustment rule. Why? So that you can get some degree of non-neutrality, some degree of rigidities, of frictions in price setting. And what we're going to find is that actually in the data, a lot of the frictions are on the repricing rule. And the adjustment rule is actually done pretty accurately. So maybe the focus on figuring out the adjustment rule, maybe we should devote more attention to the repricing rule as well. Okay. Okay, so let me skip this. Okay, so let me just give you a tiny bit about the model, and then I'll go to the information problem. Okay, so we have a bunch of retailers. I'm going to index them by J. They sell differentiated varieties, so they have market power. They're monopolistically competitive price setters in the product market, but are price takers in their input market. And as I mentioned before, once a retailer sets its price, they have to supply whatever demand walks in through the door at that price. Okay? And so the equilibrium in this economy is going to be demand determined. Right? They set a price, people walk in, they demand whatever input they need to meet this demand for their good. Right? This is going to affect the price of the input, and that's how you kind of get equilibrium through the demand side.
On the assumption of retailers have to meet demand, that this is true even if they're losing money?
Yes.
Is that a reasonable assumption?
In the short run, I think, yeah. I think one can...
They can impose a quota.
That's right. So these models have no inventories, no stock outs. So you can enrich the model with stock out and inventory motives. In this kind of baseline model, you don't have that margin of adjustment. Right? For the record, inventories adjustment is also sluggish and lumpy and imperfect and noisy. But yeah, you're right. So this is, and especially in the Calvo model, it's problematic because you have firms who haven't updated in a really long time and whose price is way out of line and who are suffering massive losses. And that's a big part of the source of non-neutrality. Whereas in this model that I'm going to talk about, with the noisy repricing, firms, they don't make that many, each individual firm is not doing that badly. It's just that in the aggregate, everybody's making mistakes, a mistake here, a mistake there, they add up, right? So that's going to be a little more appealing, I think. Okay, so, so that's what I mean by monetary non-neutrality or price rigidity. Prices don't respond, so quantities have to respond, right? It's a kind of a P times Q has to add up to 1. Okay, so here's the problem of the retailer. So retailers acquire information and set prices to solve this maximization problem. So they maximize their expected discounted, this is the discount factor, discounted profit, this is the period profit, net of the cost of monitoring conditions, market condition, to decide whether or not they should adjust their price. Okay? So there's going to be some amount of information, IA, that you obtain to figure out if you should adjust. And the cost of that information is theta A, is the parameter that we're going to estimate times A. Okay, and so you're going to keep looking out the window, more or less intensely, to figure out if you should reprice. And then if you reprice, so this is an indicator variable equal to 1 if firm J reprices in period T. If you reprice, you have to figure out what price to set. And so you're going to acquire information IP to reduce your uncertainty about what price to charge. That's going to have a unit cost theta P. We can let them be different. And in fact, in the data, they will be very different. This is going to be much bigger than this. And then, so now you figured out what price to charge, right? You get a signal about what price to charge. You have to actually implement the price. Let's put in the traditional menu cost, kappa, right? That you only pay if you change your price, okay? Okay, good. So let's talk about these information flows, right? So the information flow for the adjustment decision in period T is going to be the average Kullback-Leibler divergence of the conditional probability of changing my price if I have inherited a price P tilde, here's my tilde again, right, from the previous period, and if the current idiosyncratic state is A, so this is my own marginal cost, and if the aggregate state is gamma indexed by T, right, in the current period. Okay? So the divergence of this conditional probability relative to some unconditional reference probability lambda bar. Okay? And the information flow associated with the repricing decision, if I decide to reprice, is going to be the average KL divergence of the conditional probability of charging a price P in a particular state from the marginal or reference distribution F bar. Okay? And the cost to me of implementing F is going to be proportional to the divergence of F from F bar. Okay, and this is just the KL divergence formulas. Okay, so for a given reference, the choice distribution maximizes firm value. And I want to revisit this question of how we should specify the reference distributions that here are lambda bar for the probability of adjustment, yes or no, and F bar for the unconditional probability of charging different prices, say high versus low. Okay, so how should we specify these reference distributions? These are the distributions relative to which the cost of information is measured, right? So in principle, I could have these be whatever I want, right? I could give the firm side information. I could even make these be conditional on the state. I could say, right, like in the free recall model, these are conditional on the state, right? These reference distributions are conditional on all the actions that I've done up until today, right? So I could give the firm all that information and then just have kind of a cost that is linear in the KL divergence of the conditional from this choice distribution. I could actually also set this as a uniform, like in the control cost model. Right, so Kosten and Akov have this nice paper where they say, I'm going to make this be a constant and I'm going to make this be a uniform, exogenously specified, and then I'm going to choose a conditional relative to these exogenously specified distributions. Right? Now, as I mentioned, decision makers have very strong incentives to use sophisticated defaults, right, or sophisticated reference distributions. Why? Because these reference distributions lower both the value of conditioning on a state, right? If I'm already kind of doing pretty well without conditioning on the state, then maybe it's not worth it for me to condition on the state. And then they also lower the cost of actually conditioning on the state, because you're so close, the KL divergence of conditioning on the state is going to be pretty small, right? And in fact, like I mentioned, you want to use your knowledge of the structure of the economy. You want to use everything you know to choose well-adapted reference distributions, which from the information theoretic point of view are the ones that minimize the choices distribution KL divergence from them, right? Integrating over the states that you expect to encounter over the life of the conditional distribution. So this would be pure rational inattention. This would be, I'm sitting here, in some period, I'm re-optimizing my information choice. I'm going to look forward and I'm going to think about all the possible states that I expect to encounter going forward, right? And I'm going to design a reference distribution that integrates over all these possible states. And then in each subsequent state, right, in each subsequent state, I'm going to deviate from this reference distribution, right, little by little. And I'm going to pay, the cost is not on designing the reference distribution. The reference distribution is for free, right? I'm a computational machine. I can solve the reference distribution for free. The cost is only deviating from this reference.
And it's something that doesn't change with time, right?
Yes.
Or
it can. Right. So in the free recall, it does change with time, right? Because it evolves with the history of actions.
Not of time, also with the information.
Yes. Oh, it can also be indexed by time. It can also be just with time.
Just with time.
Yes.
Not,
so here it will not. In this model, it will not. It will be an invariant. Why do I want it to be invariant? Because I want to get this lumpiness. But in principle, yeah, you could say that the decision maker is aware of the passage of time for free, right? And so then they would choose. Like for instance, if I have persistent processes, I would certainly choose a reference that is indexed by time. Yeah. Okay, good. So here, I want to consider a less efficient reference distribution. Still endogenous, but a little simpler. And I'm going to assume that the reference distributions are the steady state cross-sectional distributions. So remember, I have a bunch of firms, right? And they're going to be in a general equilibrium, right? And I'm going to assume that these firms have lived in this environment for a very, very long time. And they've seen what their competitors are doing and, for a long time. So they've learned this kind of relatively well-adapted reference distribution that is just the cross-sectional distribution in the steady state, okay? So they might find it easy or intuitive to implement such a default rule. And this default rule shouldn't be too bad, especially in the case of small aggregate shocks, right? So this is the optimal default rule in the steady state. It's just, in the dynamics with aggregate shock, it's going to be a little inefficient. The information acquisition is going to be a little inefficient. Okay, so now let's solve the firm's problem. So think about a firm that enters a state with some price P tilde. Tilde means this price has been eroded. This is real price. This is price relative to the aggregate price index. So it's been eroded by inflation and some idiosyncratic productivity and some aggregate state, right? And I'm going to be able to choose information acquisition state by state. I choose state by state how much to condition my action on the state. Okay, so first let's solve for the probability of adjustment. That probability, that conditional probability of adjustment, lambda, is going to solve this maximization problem that's given by this V star that says, okay, with probability lambda, I'm going to adjust. If I adjust, I'm going to get some value of adjusting in this state. And I have to pay the cost, the menu cost, kappa. With probability 1 minus lambda, I don't adjust. So I'm going to continue in this state with this eroded price P tilde. Either way, no matter what, I have to pay the cost of deviating from the reference distribution, from the unconditional reference distribution lambda bar, right? What is the value of adjusting? Well, the value of adjusting depends on my repricing policy. I'm going to choose that repricing policy optimally to maximize the expected value of charging a particular price in a particular state with this probability, with this conditional probability, net of the cost of using this conditional probability and not my reference probability F bar, which is for free. Okay? The more I want to condition on the state, the bigger the cost, but of course the bigger the expected value because my price is better suited to the state. Where the value of charging a particular price in a particular state is the profit that you get in the period from that state, plus the expected discounted value of entering the next state with this new price. So now, unlike in the free recall, there's no value, continuation value of information, right? Because I don't retain information. So if you remember in the free recall problem, here, right? The continuation value depended on the full history of actions, right? I'm choosing the action today, taking into account that that I'm going to condition on this action tomorrow, right? That my prior tomorrow is going to have this action in it, whereas now I don't have that value, but I have the fact that I'm going to have this price tomorrow, right? Right? I have a continuation value from entering the next period with this price. That's going to be associated with some profit next period and some continuation value, right? And I'm not conditioning on my action today. I'm conditioning just on the state. Okay, so what do the optimal choices look like? So it's really convenient to use the log odds representation. So the log odds of adjusting when your price is P tilde and the state is A and the idiosyncratic state is A and the aggregate state is gamma is going to be equal to the log odds of the unconditional probability of adjustment plus a term, right, that is just the value of adjusting in this state, net of the menu cost, scaled by the cost of information. Okay, so now as the cost of information goes to 0, the model converges to the menu cost, the pure menu cost model, where my decision to adjust depends only on the value of adjusting, and that's it. As the cost of information goes to infinity, my decision of whether or not to adjust converges just to the unconditional frequency of adjustment lambda bar. Right? So I can nest Calvo and the menu cost model in this specification. Okay? So this is Woodford 2009. Okay? And this is very useful because then we have one parameter that governs the Calvo to the menu cost interval, so to speak. Right? Okay, and then on top of this, we now have the optimality condition for the repricing. So we now have a model where conditional on adjusting, you no longer just choose P star deterministically. You choose a distribution of prices, right, in which the probability that you charge a particular price in a particular state is high relative to the unconditional probability of charging this price. Again, when the value of charging this price in this state is high relative to the average value of charging all the prices in your policy in that state. Okay, so the F bar and the lambda bar kind of anchor the conditional distributions, right? And the more you want to condition, the more you're going to deviate from these reference distributions. Right?
When it says where the lambda bar and F bar are the unconditional steady state, that means they are determined by these things, by this lambda function and this F function.
That's right. So they're going to be, okay, so these objects are going to generate an equilibrium joint distribution of, so for example, let's take this one. it's going to determine a joint distribution of prices and idiosyncratic states, right? And then, so F bar is going to integrate over that distribution.
So you have a fixed point.
Yes. 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 So how this differs from the pure rational attention is that these reference distributions don't discount future states. Right? They don't take into account how long, they don't take into account the survival of the policy. They just look at the, what are the policies in effect right now in the cross-section. Yeah. And so, so in the algorithm you say, okay, solve for the individual decision problem, aggregate to the joint distribution of prices. I don't have that here. That's going to imply some level of price dispersion. Let's call that delta. That's going to be more price dispersion than would be warranted just by the idiosyncratic productivity term. And then equilibrium, output, wages, everything are just going to be scaled up and down by this delta. So you can have as big or as small of a macro model you want, and you just put this little pricing block inside it. So here I'm going to show you some numerical results. How am I doing? Oh, I'm doing. Okay. I'm going to show you some numerical results from kind of a baby macro model where we have some households. They have some habits to make their consumption sluggish. They have some preference shocks. So, sometimes they're a little more impatient. Sometimes they dislike working a little bit more, stuff like that. We have this competitive intermediate goods market. We have a monetary authority responding to shocks according to the usual Taylor rule that responds to deviations in inflation and in output from the natural rate. And we have a fiscal authority that just likes to spend money exogenously and then taxes people. Because, okay, so this is just to close the model.
Sorry, why do you need the fiscal authority at all?
Okay, so we don't. The reason that we use these is because we need we're going to take this model to data on the US from 1978 until 2014, end of 14. And so we need shocks to match the dynamics of output and interest rates and inflation. So this is a nice demand shock.
They're providing shocks. Okay.
Yeah. And then you can add investment, so we have bigger versions.
There are preference shocks on top of that.
Yes.
You need both.
Yeah. Yeah. I haven't even told you there are also going to be information shocks. So I'm also going to shock the thetas and the kappa. Okay, so first let's talk about the steady state. So what we do is we have data on the frequency of adjustment of price change. So frequency of price changes, size of price changes, kurtosis, all of these pricing moments that theory tell us should be informative about the degree of price rigidities in the data. So what we're going to do is we're going to target the average moments over the sample period to estimate these parameters. The unit cost of repricing, so more or less accurately. The unit cost of making the timing decision, the adjustment decision more or less accurately, the menu cost, the idiosyncratic shock, and and that's it. No. And epsilon, the elasticity, the markup. We're going to estimate the elasticity of substitution between varieties. Okay, so, and that's going to end up being 6.7, which is kind of, I would say kind of average. Typical macro models use anywhere from 3 to 10, I think. There's a lot of variability. So, okay, so basically this is the name of the game here is you're going to use outputs to try to get estimates of these unobservable costs, right, of these thetas. And, okay, so what's interesting here is that, so we have very volatile idiosyncratic shocks because we need a lot of movement in prices. That's known, that's fine. We estimate super small menu cost. And so if we didn't have information frictions, this menu cost would basically generate no real rigidity in prices. It's just really, really tiny. It's, so this is relative to, relative to the steady state output. Okay, so this is, well, actually, I'm going to show you how big this is. Okay, so this is 0.04% of steady state output. Okay? This is about an order of magnitude smaller than typical estimates of how much is spent on menu costs. Typical estimates in the menu cost models that don't have imperfect repricing, in the menu cost model with perfect information. Okay, so US data doesn't really need a menu cost model if you give it an information cost on adjustment, if you give it a hazard function that is kind of only noisily related to the state of the world. Okay, so information acquisition in total is about 2% of steady state output. And actually, a really big chunk of that is on the repricing margin, right? Which all status quo models assume is 0. All status quo models assume perfect repricing conditional on adjustment, right? And so we're actually estimating there's a lot of noise in the repricing decision. Okay. So steady state price dispersion is 13% higher. Consumption is 7% lower compared to the full information flexible price economy. So the individual pricing, I should put here the profit loss. So the individual losses to the firms are pretty small, but the aggregate loss is really quite big, 7% of consumption. I mean, so the Lucas estimate of the cost of business cycles is like, an order of magnitude smaller than this. So this is really big loss. Okay, so this is the steady state. This is kind of how severe things are on average, yeah.
In which direction does the mistake in adjustment happens? They under adjust or over adjust?
I'm going to show. There. Okay. So here I'm plotting the adjustment probability. So this is the lambda, the conditional probability of adjustment. It's a function of my existing price and the marginal cost, the A, basically, right? And so you see that if I have, what do I want to say? Okay, if I have, okay, let's start. If I have a low cost, right, I'm going to be pretty flexible here. I'm going to have pretty high probability of adjustment whenever my price is, it doesn't even have to be very high, right? But if I have high cost, right, I'm going to want to stay with high prices a lot. Now, I think what's interesting is that this isn't kind of a fixed band. This is more of a fan, right, which suggests asymmetry in the losses. So I'm much more likely to adjust when I'm underpricing than when I'm overpricing.
That's because people expect that the trend is that prices keep going up.
Yeah. Yeah. Okay, good. Yes. Two things. One, we have steady state inflation of 2%. So if you charge a high price, it's not that big of a deal. Inflation is going to erode it. And second, the losses in the profit function are asymmetric. So as I was mentioning earlier, if you charge a really low price, you could have really big profit losses. If you charge a high price, nobody comes, right? And so your losses are bounded, right? But if you charge a really, really low price, you could really get in trouble. So you're going to want to move away from that really fast. So the typical firm is going to have an adjustment hazard that is super steep when the price, so let's say this is P star, right? Is super steep when the price is low, and then super flat when the price is high. Okay. And I have another paper on this that talks about how this might have been at work during the Great Recession. Why we didn't see too much prices falling too much in the recession, and we didn't see prices rising too much in the recovery because of this asymmetry. Good. Okay, so you can get this kind of pattern if you assume menu costs are random, right? And so, in fact, in Woodford 2009, he shows a mapping, right? For any hazard function lambda, there exists a distribution G, let's call it, of menu costs, right? And so so you can have this, this mapping between information and menu costs, but it's kind of strange to think that, that menu costs are random. I mean, I think it's more plausible, at least to me, it's more intuitive to think that, that there's information costs, and that's why we make mistakes, not that menu costs are stochastic. Okay, and here's the pricing policy. So you see the noise at all levels. Interestingly, the low marginal cost guys are quite, they're the only ones who are bold enough to charge low prices, right? So if you see a sale, it's from a high productivity firm. Right? The high cost guys don't dare to go there. Okay, so just kind of summarizing, according to the steady state estimation, so to this, kind of what's the average friction like, we estimate really, really small menu costs. Now, in the typical literature, models need very, very big menu costs or exogenously low probability of price adjustment, right? Here we get infrequent adjustment, even though the menu cost is actually, really, really small. And why is that? Well, because the firm understands that it's going to make mistakes in repricing, right? And so, it decides maybe I should lower the frequency with which I adjust because I'm going to generate these mistakes. Menu cost models, as I mentioned, also need some mechanism to mute selection, right? So if everybody who adjusts has a really big gain from adjusting, they're going to adjust by, that means they're going to adjust by a lot, then you get non-neutrality, right? Then you get no bite from the price rigidity, right? And they also have a really hard time matching moments beyond frequency and size of price changes. Whereas with mistakes in repricing, you can end up with suboptimal price setting, even if the timing decision is very accurate, especially here where prices are low, right? So we estimate that the timing decision is actually, firms know pretty well when they're doing something wrong, right? They can tell that they need to change their prices. It's just, it's much harder to figure out what price you should charge, right? You know you have to do something, you just don't really know what to do, right? Okay, so now one thing that, that I can also tell you is that in the time-dependent and state-dependent literature, under full information, there's been a lot of work that shows that certain pricing statistics can act as sufficient statistics for the degree of nominal rigidity. So, for example, in the Calvo model, you tell me the frequency, I can give you the degree of non-neutrality, okay? So frequency is a sufficient statistic for the degree of monetary non-neutrality. How do we measure the degree of monetary non-neutrality? We calculate what's called a cumulative impulse response function of output or consumption to a monetary policy shock. Okay, so suppose I have, suppose the Fed, for whatever reason, just makes a mistake and sets, sets prices, sets interest rates, let's say they set interest rates too high, right? So there's going to be a shock to interest rates, to the federal funds rate, and then there's going to be some persistence to that. So this is the federal funds rate evolution over time, okay? And it's unanticipated, it's unexpected, it's just a mistake, okay? What do we expect to happen to the economy? Well, if prices are fully flexible, we expect nothing to happen to output. All the response should be on prices and inflation, right? What we see in the data in practice is we see that output kind of takes a while, but does fall, and it takes a long time to come back to zero, right? So this is the area under the curve. That is a measure of how much output responds, that is to say how much non-neutrality there is, how rigid prices are. And we can take the area, this area of the cumulative output response, and we can divide it by this area of the federal funds rate and see per unit, right, how much does output respond. And what the time-dependent and state-dependent literature has shown is that frequency is a sufficient statistic for this area for Calvo, and frequency over kurtosis, of all things, is a sufficient statistic for this area under menu cost model. Okay? So you might wonder, is it true in this model with information frictions? Is frequency over kurtosis a sufficient statistic? Why do we care? Well, because if it's a sufficient statistic, then I've totally just wasted your time. You could just ask, what is frequency, what is kurtosis, divide them, multiply by a scaling constant, and you know how effective US monetary policy is at any given point in time, right? And so, yeah, okay, so we want to know, is this a sufficient statistic result robust to information frictions? And the answer is not really. Okay, here, this is what I want to show you, the frequency over kurtosis. Okay, I call this the ALL index because the paper that found this result is Alvarez, Lobihan, and Lippi, 2016, and then they have a bunch of follow-up work, okay, where they show the ALL index is a sufficient statistic in a wide class of models with infrequent but perfect information price adjustment. Okay, so not so much in our case because of the repricing mistakes. And of course, their proof relies on perfect repricing, so it's not necessarily a surprise, but I think it kind of is a surprise just how much variability there is in the relationship between kurtosis over frequency and this area under the response function of output. Okay, so we do need a model. I didn't waste your time. And you should model information frictions because they match the data really well. Okay, so we did the steady state on average. We did some simulations to convince you that you can't really use sufficient statistics. So now let's do the dynamic estimation over time and try to answer the question, how effective has monetary policy been? Or put in other words, how severe have pricing frictions been in the US? Has there been a trend? Is there any cyclicality to it? Right? And so for that, first I need to estimate the information friction parameters and the menu cost. Are they fixed? Are they volatile? What do they look like? So what I'm going to do is take data on macro aggregates and pricing moments, estimate fundamental shocks to preferences, technologies, policies, the usual business. And then I'm also going to introduce shocks to the pricing frictions. So shocks to the thetas and to the kappa. And these are going to be interpreted as kind of, shocks to the efficiency of information processing, right? And I want to see how big these shocks are. Does the data want variability in these parameters or not? Okay. And I'm going to filter, actually not me, Camilo is going to filter these shocks. And then at each point in time, we're going to have a vector of estimated parameters, right, for the model. And so at each point in time, we can say, suppose I'm in December 1978. Given the vector of parameters that I've estimated, suppose there were an unanticipated monetary shock at that point. How would the economy have responded? How much monetary non-neutrality would there have been in December 78, in January 79, and so on? And so on. Okay? Okay, so first here are the series for the pricing frictions. Okay, so let's start with the menu cost. Okay, so menu costs, first of all, the beginning of the sample is very noisy because this is just where the estimation data starts, so measurement error is pretty big here. And I apologize for the fuzziness. I don't know why it's so fuzzy. Okay, so menu costs were very, very tiny. They were big in the 80s. Well, okay, so so why were menu costs big in the 80s and information costs on the timing of adjustments small in the 80s? Small in the 80s, right? This suggests that what was happening in the 80s was that people knew that it was time to change prices, so that's why theta L was low, but they had pretty big SS bands, right? And it literally is like it was costly for them to print out the new catalog, I don't know, of prices back then, right? So that was limiting the flexibility of prices back in the 80s, not since then. that's a good question. So, I mean, I guess you could tell a story of technological, change, that now they have scanners and they, can reprice things. They can print the menu on the printer. Yeah. I don't have a very compelling story except to say that the pricing moments in this time period suggest wide SS bands. And they suggest that firms in this high inflation environment, firms kind of knew that they needed to adjust. Right? At the same time, I think what's really interesting is that in this high inflation environment in the 80s, what price to charge was a very noisy decision. So the estimated theta P is really high. Right? And then it came down significantly. And so it seems like, okay, so the menu cost, was high in the 80s, then nothing's going on. And it seems like there's these differing trends. So theta P, the cost of repricing, the cost of figuring out what price to charge, has fallen. I want to emphasize, theta P of 1 is still big. So this is not like, first of all, this is nonlinear. The effects of theta are nonlinear. But theta P of 1 is pretty noisy pricing, right? So there's been a lot of work in the marketing literature that argues that firms have gotten better at discriminating across customers, right? Pricing policies have become more complex. We do sale, right? They do sales now, they do special promotions, all this stuff, right? So this could be consistent with that story of more refined and more discriminatory price setting. And at the same time, it seems like the accuracy with which they decide whether or not to change a price has weakened. The cost of making this decision accurately has gone up. But I do want to point out the scale. This is the low one. So this is still, pretty small change. And it went up in the 90s, and it was kind of pretty volatile. It's been pretty volatile since then. So what do these pricing moments mean for the degree of nominal rigidities, for how flexibly the aggregate economy responds to shocks? So this is the cumulative, I'm sorry, this is terribly fuzzy. It's giving me a headache. So this is this area under the curve divided by this area, the federal funds rate, right? And so again, ignore this early part of the sample. So monetary non-neutrality was high. Then it fell rapidly as theta P fell, as the cost of repricing fell. Right? Then as theta L started to rise, it rose. Right? And it's actually really, again, the scale is, this is 0.38, believe it or not, and this is 0.44. Okay. So the scale seems small, but actually this is cumulative response. In percentages of steady state consumption. So 5 basis points of steady state consumption, it's in the eye of the beholder. I don't think it's that small, right? And actually, surprisingly, monetary non-neutrality seems to go up, at least in the early part of recessions, and then it goes down. So it seems like firms don't really know what's going on, right, at the beginning of the recession, and then they adjust. Okay, so we are now trying to get data past 2014. This is not publicly available data, so all of these estimates have been based on time series that Daniel Villar gave us. He's an economist at the board, and so we're begging him to give us more recent data to see what's going on now with the high inflation environment. Oh, I'm over time. I'm so sorry. Okay, so menu costs are very small. Variation in information processing efficiency have generated significant volatility in the flexibility with which the economy responds to shocks. Timing of adjustment has been fairly accurate, and repricing has been fairly inaccurate. And just to conclude on rational attention, this has been a model of early noise in the language of Mike. And it generates a lot of discrete, stochastic, incomplete, delayed adjustment, which is exactly the kind of patterns we need in macro. Let me stop there. Apologies for